Good afternoon, everyone. Welcome to 213. It's good to see you. Just a reminder that your attack lab is due tonight at 11:59 p.m. You have one grace day for this lab, and cash lab will go out at right about the same time. Now, it's going to be a little tight for cash lab. It'll be due next Thursday, so you might want to get started on that soon. Last lecture we learned about the memory hierarchy and the idea of caching. Today we're going to look at a very important kind of cache, which are called cache memories. And they're very important to you as a programmer because they can have such a big impact on the performance of your program. So if you know about the existence of these cache memories and you know how they work, as a programmer you'll be able to take advantage of that in your programs. So last time we looked at the memory hierarchy as a collection of storage devices with smaller, costlier devices and faster devices at the top, and slower, cheaper, and much larger devices at the bottom. And then at each level in this hierarchy, the device at level K serves as a cache, holds a subset of the blocks that are contained in the device at the lower level, at level K plus 1. Now recall the general idea of caching. So we have a memory. It's an array of bytes, and we break it up arbitrarily into a collection of blocks. And this memory is larger, slower, and cheaper, and so it's much larger than a cache, which is smaller, faster, and more expensive, and which holds a subset of the blocks that are contained in the main memory. And then blocks are copied back and forth between the cache and the memory in these block-size transfer units. So, for example, if our program requests a word that's contained in block number 4, it asks the cache to return the word that's contained in block 4. The cache looks at the blocks the subset of the blocks that it's stored, discovers that block 4 is not there, so it asks the main memory to send it block 4, which it does. And then when that block arrives at the cache stores it, but potentially overwriting some existing block. Similarly, if our program asks for a data word that's contained within block 10, the cache looks, sees that it doesn't have that block, so it requests that block from memory, which copies it into the cache, which overwrites an existing block. Now, subsequently, if our program asks for a request, or if our program references a word that's contained in block 10, for example, then we have a hit, and the cache can return that block immediately without going through the expensive operation of contacting memory and fetching that block from memory. Now, there's a very important class of caches, these so-called cache memories, which are contained in the CPU chip itself and are managed completely by hardware, and they're implemented using fast SRAM memories. And the idea for this cache, which is right next to the register file, is to hold frequently accessed blocks, or blocks from main memory that are accessed frequently. Okay, so hopefully, because of the principle of locality, most of our requests for data will actually be served out of this cache memory in a few cycles, rather than from this slow main memory. Now, cache memories are managed completely in hardware. So this means that there has to be hardware logic that knows how to look for blocks in the cache and determine whether or not a particular block is contained there. So cache memories have to be organized in a very kind of strict, simple way so that the logic, the lookup logic, can be pretty simple. So there's this very, all cache memories are organized in the following way. You can think of the cache as an array of s equals 2 to the s sets. Okay. Each set consists of e to the 2e lines, where each line consists of a block of b equals 2 to the b bytes of data, a valid bit, which indicates whether these data bits are actually, the bits in the data block are actually meaningful. Right? It's possible they could just be random bits. Like, when you first turn on the machine, there's nothing in the cache, but those bits will have values, right? That they'll either be ones or zeros, but they won't actually correspond to data. Okay, so the valid bit tells us if these b bytes actually mean anything. And then there's some additional bits called the tag bits, which will help us search for blocks, which I'll show you in a minute. Now, when we talk about our cache size, we're referring to the number of data bytes that are contained in blocks. And so each cache has, there's S sets, there's E blocks per set, and there's B bytes per block. Okay, so the total cache size C is S times E times B. Okay, now so there's a lot of terms to sort of keep straight, and it's very easy to confuse the difference between lines and blocks and lines and sets. Okay, so we'll go through some examples, and hopefully these will start to make more sense. Now let's look at, in general, how the cache hardware implements a read. So when our program executes an instruction that references some word in memory, the CPU sends that address to the cache and it asks the cache to return the word at that address. And so the cache takes that address. This would be a 64-bit address in the case of x86 64, and it divides the address into a number of regions, which are determined by the organization of the cache. Okay, they're determined by those parameters: S sets, S the number of sets, E the number of lines per set, and B the size of each data block. So the low order bits, there are B low order bits which determine the offset in the block that word starts at. Okay. The next S bits are treated as an unsigned integer, which serves as an index into the array of sets. Okay, remember, we just think of this cache as an array of sets. The set index bits provide the index into this array of sets, and then all of the remaining bits, all of the remaining T bits constitute what we call a tag, which will help us when we do our search. So the cache logic takes this address, and it first extracts the set index and uses that as an index into this array to identify the set that if this block is in the set, if the block that contains the data word at this address is in the cache, it's going to be in the set denoted by the set index. Okay. So first it identifies which index to look in. And then it checks the tag. It checks all of the lines in that set to see if there's any of those lines have a matching tag, a tag that matches the tag bits in the address. Okay. and it checks to see if the valid bit is turned on. So if those two conditions hold, if there's a line anywhere in the set where the valid bit is 1 and there's a matching tag, then we have a hit. Okay, then the block that we're looking for is contained in this set. Okay, once we determine that we've identified the block, then the cache uses the low order B bits to determine where the data we're interested in begins, okay, within that block. All right, let's look at a more specific example for the simplest kind of cache, which is when E equals 1, when there's only one line per set. Okay, so E equal 1 line per set. This kind of cache is called a direct map cache. So here we have S sets. Each set consists of a single line. And now suppose our program references a data item at a particular address. The CPU sends that address to the cache. The cache takes that address, breaks it up into these 3 fields. For this particular address, the block offset is 4, and the set index is 1, and then there's some tag bits, which we'll just denote as a color pink. So the cache extracts the set index, which is 1, and then it uses that as the index into the set. And then it just ignores all the sets. If the block we're looking for is in the cache, it's going to be in set number 1. Then it does the comparison of the tag bits and the valid bits, and assume that valid bit's on and that it matches. Then it looks at the block offset, which is 4, and which tells it that the 4-byte int, suppose that's what the instruction was referencing. The 4-byte int begins at offset 4. So now the cache takes this int and it sends it back to the CPU, which puts it in the register. Okay. Okay, if the tag doesn't match, then the old line, if the tag doesn't match, then there's a miss. And in that case, the cache has to fetch the corresponding block from memory, and then overwrite this block in the line. And then it can get the word out of the block and send it back to the processor. Okay, now let me ask you a question just to check to see if you're following along with this. So if there's a miss, and the cache has to request the block from memory, fetch it from memory, and then overwrite the block in the current line, does it also have to change the tag bits? Or do those stay the same? So do the tag bits that were in this line get overwritten with a different value? Or is it the same? Same? Different? Same? Different. Now, why would it be different? We haven't changed. Yes? I'm sorry?
The old one might have had a different tag.
Oh, it almost certainly has different data. But does it have a different address?
Well, you missed because the tag didn't match. So the tag is the thing that you missed, a different tag. So you need to figure it out.
Exactly. It missed because the tag didn't match. If the valid bit was false and the tag matched, then that would also be a miss. Oh, then you wouldn't. Okay, that's right. That's okay. Good. Okay, great. All right, let me do a really simple, specific example of how a direct map cache works. I want you to to understand in real detail how this would work, but I also want to make a point about the weakness of direct map caches and why you would want to have more than one line per set. Okay, so this is a really simple, our memory system consists of 16 bytes. Okay, so it's not a very useful system with 4-bit addresses. And it's broken up into blocks of 2 bytes each. Our cache consists of 4 sets with 1 block per set. Now, our 4-bit addresses, because b equal 2, that's 2 to the 1, we only need 1 block offset bit. Right? There's only 2 bytes in a block, so the byte we're looking for is either a 0 or 1. Okay. Because we have 4 sets, we need 2 set index bits, and then the remaining bits are always tag bits. So in this case, there's just 1 tag bit. All right, now let's suppose that our program executes instructions that reference the following memory addresses: 0, 1, 7, 8, and 0. And these references are reads that they're reading 1 byte per read. Okay, like I said, this is a really simple system. So let's look at what happens now. We start out initially our cache is empty. Valid bits are all set to 0. And now the cache receives a request for the byte that's at address 0. So it extracts the set index bits, which in this case are 0, 0. So it's going to look in set 0 for, and in this case, since valid is 0, it's a miss. Okay. So it fetches that block from memory, sticks the block. So this memory, this is using array notation for memory. So this is like the bytes that extend from offset 0 to offset 1 inclusive in memory. Okay. The tag bit is 0, and the valid bit is 1. Okay, now the next address that comes by is for address 1. Well, that's a hit, right? Because the block that contains the byte at address 1 is already in the cache. The tag and the tags match. Okay, so we're good. That's a hit. Okay, now we get address 7. So the cache extracts the set index bits, which in this case are 1, 1, or 4, or 3 rather. Looks in set 3. There's no valid bit. So that's a miss. And it loads the data from memory that spans bytes 6 and 7. And in this case, the tag bit is 0. Okay, so we record that in our metadata. Okay, the next reference that comes by is 8. Now 8 has a set index of 0, 0, 0, but that's currently occupied by block 0, 1, and we can tell that because address 8 has a tag of 1, and the existing block, the block at the earlier address, at address 0, has a tag of 0, so that's a miss. So now we have to go fetch the block containing byte number 8 into memory. So now we have bytes 8 and 9, and our new tag bit. Okay, now the next instruction is for byte 0. And we had that in our cache, and we just replaced it. Okay, so it's another miss. So that's unfortunate. And the only reason we missed it is because we've got just 1 line per set. Right, so we were forced to overwrite that block containing bytes, the block 0, 1. When we missed on block 8, 9. Okay, so this, And you see there's plenty of room in our cache. We've got two lines that we haven't even accessed, right? So our cache is plenty big, but just because of the low associativity of our cache and the pattern, the access pattern that we were presented with, we've got a miss that really was kind of unnecessary. So, oh yes, sorry.
Can you explain why the loss values at 3 and 6 and 7?
Should be 7 to 8.
Like how you know that those 2 bytes are there?
6. So when we referenced 7, it's actually it's at offset 1 in that block 6, 7. Okay, since our blocks are 2 bytes, they'll always start on an even multiple. Okay. Any other questions? Okay, so this sort of is the reason why caches have higher associativities, higher values of E. So let's look at, and so for values of E greater than 1, we refer to them as E-way set associative caches. So here E equals 2, so it's two-way associative. So let's suppose we have a two-way associative cache. So here we have our array of sets, and now each set contains 2 lines, okay, instead of 1 line. And suppose we're presented with an address with the following form. We're looking for a word that begins at an offset of 4 inside our block within set number 1. Okay, so the cache extracts that set index. So this is set 0. This is set 1. This is set 2. Okay. Throws away all the other sets. And now in parallel, it searches the tags. It searches for a matching tag in both of these lines and a valid bit. So if we get a matching tag and a valid bit true, then we've got a hit. Now yes. Yes.
How does it do it in parallel? Like if we have 2 processes, we normally do it. What if we have a lot way too many?
Oh, it's a very good question. So there's hardware logic that does that compare, and that's the reason that as the associativity goes up, that logic gets more and more expensive. Okay, it's like you're kind of doing some kind of tree search, and so that actually is the limit. That's why, because in general, right, if you take this to the limit, there's just one set with. We call that a fully associative cache. So there's just one set, and now a block can go anywhere, right? There's no constraints now on where you place a block. But because of the complexity of that fully associative search, those are very rare. In fact, we'll see fully associative caches, but they're software caches. Okay. So in software, so the complexity of the hardware and sort of it's not worth the complexity of the hardware for the penalty of having a lower associativity. Okay, but there are some systems later on when we study virtual memory. In a virtual memory system, the DRAM serves as a cache for data stored on the disk. And as we saw last time, the penalty for a miss, if you have a cache on DRAM and you miss and you have to go to disk, the penalty is huge for that. And so because of that, it's worthwhile having very complex search algorithms. And in particular, in a virtual memory system, the DRAM is implements a fully associative cache where blocks from disk can go anywhere. We'll get into that later when we look in virtual memory. But you're right, you'll see in real systems nowadays that the number goes up, right, because feature sizes are going down and designers can afford to implement more expensive hardware. But the largest associativity on Intel systems that I know of is 16-way associative L3 caches. And then the others are 8-way associative. So that's sort of the order of magnitude that's state of the art right now. Okay, so then once we've identified a match, we use the set offset bits. In this case, we're accessing a short int. So 4 is the offset within the block of this, the 2-byte short int, which then we can return to the processor. All right, so let's do that same simulation that we did before, but this time with a 2-way associative cache. Now, memory system is the same, but now instead of 1 set, we have 2 sets. And, instead of 4 sets, we have 2 sets. So the cache, this is the same sized cache, but we're just going to organize it differently. Okay, instead of a direct map cache, with 4 lines, containing 4 lines, 1 line per set, we're going to implement a 2-way associative cache where we have 2 sets with 2 lines per set. Okay, so in each case there's 4 total lines. Question?
I just have a question quickly on the previous thing. How did you know that you're just looking for 2 byte loops as opposed to like the all 4 bytes?
Oh, so that comes in with the request somehow. And I actually don't know the details of that. It may, I guess it could ask for there could just be a default size. Maybe it's always a 64-byte word and then the processor extracts the current bits. I actually don't know the details of that. But it either comes in on the request or there's a standard size that the processor then parses out. We'll just assume that the cache knows what size to return. Yes? How do you decide which block to replace? That's a really good question. So there's a lot of different algorithms. The most common algorithm, or a common algorithm, is least recently used. So by locality, you want to keep blocks in the cache that are being used a lot. And so if a block isn't referenced for a long time, by the principle of locality, by sort of the inverse locality principle, it's likely not to be referenced in the near future. So that's one algorithm that you just keep track of. And I'm not showing there needs to be additional bits in the line to sort of keep like sort of virtual timestamps. But that's sort of the general way you do it. Just try to keep the blocks that are being accessed the most frequently, the most recently. Yes? Okay, the question is, what determines the block size? That's determined by the design of the memory system. So that's a fixed parameter of the memory system. So when the Intel designers decided to put cache memories on their processors, they decided that the block size would be 64 bytes.
But they are in agreement with the number of lines per set.
Sorry?
So they are in agreement with the number of lines per set.
So the block size comes first. Then you determine how big you want your cache to be. Okay, and you determine the associativity. Okay, and then once you've determined the associativity and you know how big your cache is, then that determines the number of sets. Okay, so basically all of those, the number of lines and the capacity, the number of lines per set is sort of a fixed high-level parameter, design parameter. The size of the cache is a high-level design parameter, and then the number of sets then is induced from that. Okay. Yes.
For a line, so for a set with multiple lines, and there's a miss, how does it choose which line to overwrite?
That's the replacement policy. How does it, so the question is, how does it, when there's multiple lines in a set, how does it determine which to overwrite? And that was the previous question. Maybe I should have repeated it. So you try to pick a line that was least recently used. So lines that haven't been accessed recently are good candidates for replacement because of this sort of inverse locality principle, right? That they haven't been referenced recently, chances are they won't be referenced. Again, oh yeah, there's additional bits that I'm not showing here that you have to. So when you replace a line in the set, if that data has changed, then it has to be written back to memory. And that's another bit I haven't shown. Yes?
So you said that the block size is 64 bytes, but if we're only referencing integers, or if we're only generally referencing small like words, why is the block size so big relative to that?
Ah. So this is a really tricky parameter, right? And it's a high-level system parameter that it goes on for years. So the idea, you want to have blocks in order to exploit spatial locality. Right? Think about it. If you're going to go to the trouble of, if you have a miss in cache, and you're going to go to the trouble of going all the way to memory to get some data, you want to amortize the cost of fetching that data by fetching more than one byte. That's the motivation for blocks. Because by the principle of locality, and spatial locality in particular, if you reference a word inside of a block, chances are you're going to reference a nearby word, which will also be in that block. Okay, so blocks, the whole purpose of blocks is to exploit spatial locality. Now, if you make your block too small, then you don't amortize, you don't get the same amortization, right? You maybe get one, you bring the block in, so there's a reference, you get a miss, you bring the block in, there's another reference nearby, you get a hit because the block's in memory. But then the next reference is in a different block because your block sizes are too small. Right? So you kind of want to make blocks big as possible, but without slowing the system down. So if you made your block size too big, it would just take too long to bring that block in. Plus now your blocks are taking up bits in your cache memory. So now there's no room for other blocks, right? So it's a really tricky design problem, right? And if we're taking an architecture class, then we would sort of dive into the, how architects make those design decisions. But in general, it's kind of a balancing act, right? Were there any other questions? Yes?
Every time there's a miss, do you always have to overwrite a line, or can you directly increment it?
Oh, the question is, every time there's a miss, do you have to select a victim line and overwrite it? Yeah, I don't know of any caches that don't do that. Now we'll see when we look at writes. We'll see there's an option of whether we're only looking at reads right now, but with writes that question does come up. Okay, and if you wait in a couple of slides, we'll go over that. Any other questions? Okay, so let's look at this two-way associative cache now. There's one block offset bit. We only have two sets, so we only need one set index. And then the remaining two bits are tagged. So let's go through our trace. So address 0 is in set 0, right here. That's a miss. So we load that into memory. The reference to address 1, that's in set 0, and that's a hit because that byte is in our block. The reference to 7 is a miss. That's in set 1, so we load that. And we were just randomly pick one of these to overwrite because the cache is empty. The next reference is to address number 8, which is in set 0. Now here's the difference between the direct map cache and this two-way set associative cache. When we reference address 8, that block the corresponding block has to go into set 0 because of this 0 set index bit. But we've got room now because our sets have room for 2 lines instead of 1. So when we load that in, if we have an available empty slot, we'll put it there. We won't overwrite anything, right? So if possible, we'll always try to overwrite empty lines. So now we've got, in this set, we've got block 0, 1 and block 8, 9. So when we get our reference to to address 0, whereas before when we had a conflict miss in the direct map cache, now we can satisfy that request. It hits in memory, and the cache can satisfy it from the cache instead of going to memory. Okay, does that make sense? Okay, now what about writes? So there's multiple copies of the data, right? We're subsetting, as we move up the hierarchy, we're creating subsets of the data in the caches. So what do we do if we do a write to a word within a block that's currently in the cache? Okay, we have 2 options. We can write that block immediately to memory, right? We've got a block that's like this big, and we're updating a little chunk of it. So we can either do the update and then flush it to memory immediately, so that memory always mirrors, the contents of memory always mirror the contents of the cache. Okay. But that's expensive, right? I mean, memory accesses are expensive. The other option is what's called write back. So in this case, when we write to a block in the cache, we don't flush it to memory until we elect that particular line as a victim that's going to be overwritten. And only then when we sort of defer the writing to memory until the last possible minute. We defer it until just before the cache would overwrite that data block. Okay, so that's called write back. And for write back, you need to have an extra bit in the line that indicates whether that block's been written to. So the algorithm is when the cache identifies a particular line to overwrite, it checks the dirty bit on that line. If it's set, then it writes that data back to disk. Okay. If that block hasn't been written, there's no need to write it back because it has the same value as the copy of the block on disk. Okay, now, so that's a write hit. Now what happens if we have a write miss? So we're doing a write to memory, and the word that we're writing is not contained in any block that's in our cache. Okay. So we have 2 options. We can do what's called write allocate. So we can treat it, if there's a miss, we can do sort of the symmetric thing that we did with a hit, which was create a new line, possibly overwriting an existing line, and then write in. So we could create that cache entry, that cache line, fetch it from memory, and then do the write. Okay. So this is sort of symmetric to reads, right? So every write, if it misses, when the write finishes, that block will be in the cache. And if we do a subsequent read, we get a hit. Okay, so that's the reason you might want to do that. The other option is just to don't allocate an entry in the cache, don't allocate a new line, just write the data directly to memory. You don't really need to understand the distinction between these 2 things. Different caches use different policies. For your own mental model, a good model to use is just to assume write back, write allocate. So just assume that we won't copy the data to disk. If there's a hit, we won't write it back to disk until the last possible minute. And every time there's a write miss, we'll create a new entry in the cache. Okay, so I think that's sort of the simplest model and it's a reasonable model that you can use regardless of the particular cache implementation. Now in a real system, so far we've only assumed that there's a single cache, but in real systems, there's multiple caches. So modern Core i7 Haswell architecture from Intel contains multiple processor cores. So 4 is a typical number for like desktop systems. 8 to 12 is typical for server class systems. These processor cores can each execute their own independent instruction stream in parallel. And each processor core contains general purpose registers, so that's level 0 in the cache. And then 2 different kinds of L1 caches. The data cache, the L1D cache, and the I cache, which is the instruction cache. And these are fairly small, 32K bytes. They're 8-way associative, and they can be accessed in a small number of cycles. The next level of the hierarchy is an L2 cache, which is still fairly small, 256K bytes, same associativity, and it has a slightly longer access time. And it's unified in the sense that the L2 cache contains both data and instructions. Okay. So that's all within a single core on the chip. And then also on the chip, but external to all the cores and shared by all the cores, is an L3 unified cache, which is 8 megabytes and 16-way associative, with an access time that's like 40 to 75 cycles. So if there's a miss in L1, then the L1 sends a request to L2 to try to find the data in L2. Since L2 is a little bigger, maybe the data hasn't been flushed out of L2 yet. If L2 can't find it, it sends a request to L3 to see if it can find the data in L3. If L3 can't find it, then it gives up and it goes off chip to memory. Yes, question?
Is the main memory the same as the RAM?
Yes, main memory is it's the DRAM, built of DRAM chips. It's separate. It's in a separate set of chips on the motherboard, connected by those that I/O bridge and the various buses that we talked about last time. And for all of these different caches, the block size is 64 bytes. Now, there's a number of different ways to think about the performance of caches. My most common way is using a metric called the miss rate. So this is the fraction of references that miss. So it's 1 minus the hit rate. So for caches to work, the miss rate has to be pretty low. Okay. And fortunately, because of locality, these miss rates are low. Another metric is the hit time. So if we do have a hit in the cache, how long does it actually take to sort of look up do the lookup to determine that there was a hit and then return the value? Okay. So for L1 in an Intel system, this is 4 clock cycles, 10 clock cycles for L2. And then there's an additional cost. So you always have to pay the hit time, right? The hit time is the best you can do. But if you have a miss, then you pay the hit time because you have to do the search, and eventually you're going to have to return the word back to the requester. But then you have this additional cost, which is going to the memory to fetch the data. Okay, so that miss penalty, that so-called miss penalty, is on the order of hundreds of cycles for main memory. But at other levels of the hierarchy, it can be huge. So the miss penalty, if you have a cache in main memory that's caching blocks that are stored on disk, the miss penalty is enormous. So it's kind of interesting if you think about it that the performance of these systems is very sensitive to the miss rate, much more sensitive than you would think. And in fact, 99% hit rate is twice as good as a 97% hit rate. Yes?
Yeah, so the latency I want to how to tag, does it incorporate the latency to access the tag? Because we need to first check the tag and then to look at the data, even if it is
Yeah, the hit. So the question is, does the hit time include the time to access the tag? And yes, so the hit time is the time it takes to search to determine if that item is in the cache and then return it.
So in that sense, if it is a cache miss, then basically the whole time to improve would not consider like some. So basically, it will include the type of cap latency and the memory access.
Yeah. So the miss penalty is the time it takes for the cache to fetch the data from memory. So that's all the latency, going across the buses, the time it takes the memory to respond to the request, the time it takes the data to flow back over the buses back to the cache. So the time for a miss is going to be the hit time plus the miss penalty. Is that clear? So, imagine, suppose there's a hit time of 1 cycle and a miss penalty of 100 cycles. Those are reasonable numbers. So the average access time, if you have 97% hits, it's the hit time plus the percentage of misses times the miss penalty. So that's 4 cycles for the average access time. But if we just increase the hit rate by 2%, the average access time drops by 50%, a factor of 2. All right, so why is this stuff important? Why should you care about it? So caches, as we've seen, are these they're automatic. They're all built in hardware. There's no part of the sort of the visible instruction set that lets you manipulate caches in your assembly language, machine code and programs. So that it all happens behind the scenes automatically in hardware. But if you know about the existence of caches and you have this general idea of how they work, then you can write code that's cache friendly in the sense that your code will have a higher miss rate than code that isn't cache friendly. So the idea is you want to focus on making the common case go fast. Don't spend your time on code that doesn't get executed very much. So look at the most commonly called functions, and then within those functions, look at the inner loops of those functions, because it's the inner loops that are executing the most. Right? So you can, as a first approximation, you can just ignore sort of stuff. If you have nested loops, you can ignore stuff that's going on in the outer loops and just focus on the code in the inner loop. Now what you want to do is try to minimize the misses in the inner loop. Okay, so repeated references to a variables are good, especially if those are local variables. Right? So remember, if you declare a local variable in C, the compiler can put that in a register. Right? If you're referencing global variables, maybe not. The compiler doesn't know what's going on, so it can't put the reference to that variable in a C in a register. Okay, so repeated references to local variables stored on the stack are good because those will get turned into register accesses. You'll never go to memory. Okay, also stride 1 accesses to arrays are good. And they're good because of the existence of these blocks. Right? So the only way you'd know that stride 1 references are good is if you knew that caches have these 64-byte blocks. Okay, so and stride 1 reference will have half the miss rate as a stride 2 reference. Right? Because if you're doing stride 1 references, the first reference to a word in a block will miss, but then subsequent references will hit. Right? And you'll hit, if you're doing a stride 1 reference, you're going to hit every word in that block. If you're doing stride 2 references, you're only going to hit every other word. right? So you get sort of half the, so you'll miss at twice the rate. So, so basically the point I want to make to you is that our understanding of caches allow us to sort of quantify this qualitative notion of locality that we developed the last time, right? The last time we said if it's doing stride 1 references, that's good. If we're accessing the same variable over and over, that's good. But if we understand caches, now we can quantify it in terms of miss rate. All right, so let's finish up the rest of the class. We're going to look at the performance impact of caches on your code, okay, and why you need to know about these things, and the impact that they can have. So there's a very interesting function that's actually plotted on the cover of your textbook that we call the memory mountain. I learned about this from a graduate student here at Carnegie Mellon back in the 90s who developed this notion, named Tom Stricker. And what it is, the memory mountain plots a measure called read throughput, or read bandwidth, which is the number of bytes read from memory. So if you have a loop and you're scanning over a vector, so you have a vector of say double words, and you're reading those elements from a vector one after the other, the read throughput is the number of megabytes per second that you can perform that task at. And the memory mountain plots read throughput as a function of the temporal and spatial locality in that loop. Okay, so in a sense, it's looking at a wide range of locality options or characteristics in a program, and it's plotting the performance of that memory system on that across that range as a two-dimensional function. So in some ways, the memory mountain is a kind of a fingerprint, right? Every system has its own unique memory mountain that we can measure, right, by writing a simple program. And so the idea here is that to construct the memory mountain, we write a program called test. Oh, shoot. For some reason, it's not. Okay. All right. So when we build a memory mountain, we're given a vector that consists of a collection of double words. And then we write a loop that reads those words, that reads some number of words, in this case, there we go. So it reads elms, number of elements, right? So we've got each of these double word elements with a stride of stride. Okay, so if we have a stride of 1, I know that was kind of redundant, huh? So if we have a stride of 1, then we'll have our loop will sort of loop through and read these elements until we've read elm's number of those elements. Okay, and then we'll do it again, and then that warms up the cache. Then we do it again and do exactly the same thing. So if we're doing this with a stride of 2, then we would read this word 0, or LM2, LM4, and so on. Okay, so all we're doing, we're just for a wide range of strides and a wide range of sizes, we're scanning over this vector and just recording how long it takes to do that read. And then we convert that into megabytes per second. And in order to, I just wanted to show you this. We're not going to go into detail about this, but this is actually how I generated the cover on the book. And in order to exploit the parallelism inside the Intel processor, like you learned about last week, there's a lot of parallel functional units. In order to exploit those, I did 4x4 loop unrolling. So I'm actually doing sort of 4 scans in parallel. But the general idea is just what I've showed you here. And this 4x4 loop unrolling is just an optimization. But I wanted to show it to you because it's the exact same principles you learned about last week when Professor Bryant talked about code optimization. So what we do is we call this test function with these various ranges of elms and stride, and then we measure the performance, and we get this beautiful picture, this beautiful function. To me, it's beautiful. I don't know. Does it look beautiful to you? So on our z-axis is plotting read throughput in megabytes per second, ranging from 2,000 megabytes per second up to 16,000 megabytes per second. This axis is stride, so going from stride 1 up to stride 12. And this axis is, so as we increase stride, we're decreasing the spatial locality. All right? And this axis is the size axis. So we're going from, I think, 16K up to 128 megabytes. So this is the number of elements we're going to read each pass through. So as we increase the size, we're sort of decreasing the impact of temporal locality because as we increase the size, there's fewer and fewer caches in our hierarchy can hold all that data. And so we've got spatial locality decreasing in this direction and temporal locality decreasing in this direction. So as a programmer, what you want to do, you want to be up here. Right? Good spatial locality, good temporal locality, because you can get like 14 gigabytes per second measured read throughput. You don't want to be down here, which is only about 100 megabytes per second, where you're reading out of memory. Right? So the difference between reading all of your data from memory and or reading it from some part of the caches is huge. It's enormous. Okay, so because you're 213 students, you'll be up here, and all the students that didn't take 213, they'll be down here. And I've actually had people, several people write back to tell me about their experiences, in internships and jobs after they left CMU, where they were given some code that was down here, and they recognized the locality issues, and they got it, better up here, or close, at least better. So this picture, this so-called memory mountain, has all kinds of interesting features. First of all, there's these, what I call ridges of temporal locality, where these ridges, you see these ridge lines? If you think of this as like a mountain, you see this ridge line, and you see this ridge line, and here's another ridge line, and then here's another one. These correspond to different levels in the hierarchy. So this top ridge line is where you're reading directly out of L1. And it should be perfectly flat. And it's so fast that we're getting like measurement jitter, performance jitter, right? But and this little drop off here is a measurement artifact. It shouldn't be there. It should be flat and go all the way to the wall back here. And then here, this ridgeline is where we're accessing L2. This is where we're accessing L3. And here's where we're accessing mostly from memory. So you have these ridges of temporal locality, and then you have these slopes of decreasing spatial locality. So you see this slope here? As we're moving from the top of this slope down to the bottom, we're decreasing our spatial locality, so we're getting less benefit for these blocks that we're bringing in. Right? So you can see we're getting less benefit out of the cost that we went through of fetching these blocks. And once the stride hits the block size, now every reference is hitting a different block, and so then it flattens out. Then you're getting no benefit from spatial locality. And similarly, here's where this slope is where we're reading from L3, and it flattens out. They always flatten out at the block size, which is a stride. These are double words, right? So it's stride of 8 is 64 bytes. So once you exceed a stride of 8, then you're no longer you're missing every time in a different block. And there's this interesting. This one puzzled me for a while. You might be wondering, like, how come? Like over here, as we increase the size, we're sort of getting the, as we increase the size, we're doing most of our references out of caches that are lower in the cache hierarchy. Okay. But except when we're doing stride 1 references, you can see all the way up to right at the end, right before it exceeds the size of L3, it's flat. Okay. And it's running at the L2 rate. Right? So here's the L1 rate, and then it drops off. And then it's running at a constant L2 rate until the data no longer fits in L3. And so I think what's going on here is that the hardware, the L2 cache hardware is recognizing, or maybe it's an L1, but some logic in the cache system is recognizing this stride 1 reference pattern, right? Because it sees all the addresses. It's recognizing that stride 1 pattern, and then it's aggressively prefetching from L3 into L2, so it's fetching ahead of time. It's anticipating. It's saying, look, I've gotten 5 stride 1 references in a row. I'm going to go grab a whole bunch of blocks and load them all up, because by the principle of spatial locality, those blocks are going to be referenced in the near future. So this was really neat, and this only happened within the last couple years. So the Intel engineers are always hard at work, and maybe by the time we do the next edition of the Memory Mountain, those systems will recognize stride 2 and other stride patterns too. But from this data, it appears that it's only recognizing stride 1. Okay, so we can improve the spatial and temporal locality of our programs in several different ways. One way to improve the spatial locality is to rearrange loops. And I'll use matrix multiplication as an example. So here's a sort of a simple matrix multiplication code where we're multiplying A times B and adding it. We're taking what's in of the ijth element of C, and then to that we're adding the sum, the inner product of row I of A and the row J, column J of B. Okay, and then so we're going through, and for each ij in this matrix C, we're computing an inner product and then creating that sum. So we can actually Turns out there's a lot of different ways to do matrix multiply. And we can permute these loops in any of 6 different possible permutations. So this is a permutation where it's I followed by j followed by k, but 5 other possibilities are feasible. And so we can actually analyze those different permutations and predict which one will have the best performance. Okay. So what we'll do is we'll look at the inner loop, and we'll look at the access pattern of the inner loops, and it's in the access pattern on arrays C, A, and B. Okay. So let's look at the IJK implementation that I just showed you. So as always, we focus on the inner loop. And if you notice, this inner loop is doing a row-wise access of column A and a column-wise access, a row-wise access of array A and column-wise access of a row B. So row-wise of A, column-wise of B. We don't really care about C because it's not in the inner loop. Okay, so just ignore that. So given our assumption that we can hold, in this case, we're assuming that we can hold four of these integer elements in one block. So the row-wise access, which has good spatial locality, will miss 1 every 4 accesses. Okay, the very first reference will miss, and then the next 3 will hit. And then the next reference after that will hit a new block. Okay, so 1 out of 4 references to A will miss. But because the access pattern for B is column-wise, every reference to B will miss. Okay, so the average number of misses per loop iteration is 1.25. Okay, the JIK version is exactly the same pattern. KIJ is a little different. Here, we're doing row-wise access of B and a row-wise access of C. So that's good, right? So now we've got stride 1 accesses on both B and C, and the reference to A is outside of the loop, so we don't care about it. So both B and C will miss 1/4 of the time. Okay, so the total average number of misses per loop iteration will be 0.5. That's pretty good. And IKJ has the similar behavior. Now JKI is sort of the exact opposite. JKI does column-wise access of A and column-wise access of C. So we know that's a stinker, right? And we qualitatively know it's bad, and we can compute that it'll miss 1 time per loop iteration. So that'll be total of 2 misses per iteration. And KJI has the same bad pattern. Okay, so if we look at all these permutations, you can see that IJK and JIK miss 1.25, have 1.25 misses. KIJ has 0.5 misses, and JKI has 2 misses. So clearly it looks like KIJ and its brethren are the best option. The only difference is that KIJ has this additional store, so there might be a question of, is that going to slow things down? Well, it turns out in systems, in storage systems, writes are much easier to deal with than reads. Can you think about why that might be true? So writes, you have a lot more flexibility than you do with reads. I mean, yes? That's exact. Yeah. So you have options. You can write back, defer. You can defer writing until the value that you've written is actually used. But when you read an item, you're stuck. You can't do anything until you get that data. So it turns out that writes don't really. This additional store doesn't really hurt us. And so when we measure these on a modern system, you can see that the KIJ, which has the fewest number of misses, has, you see, we're getting like 1 miss. What we're plotting here is cycles per inner loop iteration. So each each iteration is taking about 1 cycle, which is really good. This IJK pattern, which was kind of the intermediate, 1.2 misses, that's sort of in between. And the JKI, which has 2 misses per iteration, is the worst. Okay, so what's interesting is we could actually, just by doing a little bit of analysis, simple analysis, we could actually predict what this graph would look like. Okay, in the last 10 minutes of the class, we're going to look at how to improve temporal locality. Now, so what we did when we rearranged our loops in the matrix multiplication, what we were doing was improving our spatial locality, right? But we didn't really do anything to improve the temporal locality. To improve temporal locality, you have to use a technique called blocking. And this is important to understand because you're going to need it in your cache lab, for one thing. But it's also a very general technique anytime you're having issues with temporal locality. Okay, so we're not going to go into too much detail of this code, but what I did, I rewrote the matrix multiply so that it operates, a 2-dimensional matrix, you can really just think of it as a contiguous array of bytes. So I just rewrote this code to operate on a contiguous array, a 1-dimensional array. And then I'm doing the indexing explicitly here. So here, C I times n plus j, this is an n by n matrix. What I'm doing is I'm computing where the ith row starts, and then I'm going to the jth column of that row and then accessing that element. All right, but it's the same idea as before. So let's look at the miss rate for this. This is just our original unblocked matrix multiply. So what we're doing is we're computing C00, and we're doing that by taking an inner product of row 0 and column 0. Whoops. So if you look at we're assuming that the cache blocks hold 8 doubles and that the matrix elements are doubles, then we're going to miss 1/8 of the time. Okay, so in the first iteration, we're going to miss, the first iteration does n of these things, and since we're missing n over 8 of the time, we're missing 1 block for every 8 references. For the first iteration, we're going to miss n over 8, and since there's n for each element, for each block, and then, so this is the number of blocks and the number of misses, and then we have n elements. So that the total number of misses is 9 over n divided by 8 misses for the first iteration. Okay, the second iteration will have the same number of misses because of our assumptions about the size of this array. So these rows are way too big to fit in the cache, so we don't get any temporal locality. Okay, so the total number of misses is 9n over 8 times the number of elements that we're updating, which is n squared. Okay, so our total misses is 9 over 8 times n cubed. Now let's rewrite the code to use blocking. And so you can look at this code later, but it's much simpler just to look at it pictorially. So what we're doing, instead of updating one element at a time, we're updating a subblock, a b by b subblock. And we're doing that just totally analogously to when our original case where b equal 1. This b by b subblock in C is computed by taking an inner product of the subblocks of a set of subblocks in A with a set of subblocks in B. And for each one of those, we're doing a little mini matrix multiplication. So we're taking this subblock times this subblock plus the second subblock of A times the second subblock of B plus the third subblock of A times the third subblock of B, and so on. Okay, so we're doing the same inner product operation, but instead of on scalars, we're doing it with these little tiny matrices. Okay. All right, so let's look at what happens to the miss rate when we do this. So there's n over b blocks in any row or column. And since there's b squared items in each block, b times b, there's b squared over 8 misses for each block. Okay. And so then since there's n over b blocks in each matrix, and there's 2 matrices, there's 2n over b times b squared over 8 misses for this first iteration. So that works out to be nb divided by 4. And the second iteration has the same miss rate. So the total number of misses is the number of misses for each iteration times the number of elements in C that we're updating, okay, which is n over b squared. So that all works out to, it's n cubed divided by 4b. So in our first case with no blocking, although the number of misses is asymptotically the same, but there's this big difference in the constant factor. So for no blocking, it's 9 over 8. For blocking, it's 1 over 4b, where now we can just sort of drive that down by increasing the block size. So this gives us some control. But we can't make the blocks too big because we need to fit 3 blocks in cache at any one point in time. Okay, so the reason, this is a dramatic difference, right? And the reason for this is that by doing the blocking, we're sort of exploiting, once we load a block into memory, we're sort of reusing its items over and over again. So we're exploiting more temporal locality. And matrix multiplication has this implicit locality because the computation is order n cubed, but the size of the data is n squared. Right? So we must be reusing some data items. Right? The problem with our scalar approach is that when we were reusing them, they weren't in the cache. Okay. All right. So the point that I wanted to make with you is that cache memories, although they're sort of built-in automatic hardware storage devices, and you can't really control them, if you know about them, you can take advantage of your knowledge and exploit them and make your code run faster. Okay, and the way you do this is, like I said, focus on the inner loops. Try to do accesses that are stride 1, and try to maximize spatial locality, and try to maximize temporal locality by reusing local variables, which can then be put into registers. Okay, so that's it for today. Good luck with your attack lab if you haven't finished it, and don't forget to get started on Cache Lab this weekend.